This is Unit 5, Note 3. Today we're going to talk about definite integrals and limits of Riemann sums. So we're going to take our talk from yesterday on Riemann sums and just go a step further with it. So this is very similar to the picture that we started with yesterday on Riemann sums. We're going to generalize things today. So let's consider a right Riemann sum. And we're using a right Riemann sum to approximate this area under this curve, right? So we're still approximating this integral from a to b of f of x dx. So I'm going to use rectangles, and I'm going to try to make each of my base lengths the same. So in my drawing, I may or may not be successful in that, but let's assume that I'm making every base length the same. And I'm going to call every base length delta x. So every base length here is delta x. Okay, first of all, let's get an expression for delta x in terms of a and b. So delta x will be, in class I would let you guys come up with an expression for delta x. Delta x would be b minus a divided by however many rectangles we have. So let's let n equal our number of rectangles. So delta x would be b minus a, whatever that is, divided by n. It just makes sense. All right, the distance from a to b divided by the number of rectangles that we have, if we have all of these the same. So every delta x is going to be that. Now we have a way to write every base length of each rectangle. Now we need a way to write every height of the rectangle. Well, if we're using a right Riemann sum, then this will be the height of the first rectangle. I'm going to draw it out over here. So that would be the height of that first rectangle, right? So that height, let me get a different color here. That height, how can we write that height? It's definitely the y value of this function. So that would be f of what? F of what? What is that x value? Well, that x value is, we started with a and we added delta x to it, right? So that would be a plus delta x. The next rectangle height would be right here. Okay, so far our first rectangle has base length delta x and height f of a plus delta x. In fact, I think I'm going to write that up. If I'm adding up all the areas, in fact, let me just go ahead and write that. Integral a to b of f of x dx is approximately equal to, my first base length is delta x times the height would be f of a plus delta x. Okay, and now I'm going to go to my next rectangle. Well, my next rectangle also has base length delta x, because every base length is the same. Then I have f of, okay, so this height right here is f of what? What is that x value? What is this x value right there? Well, it's a plus 2 times delta x. So a plus delta x times 2. Okay? And then we go to the next rectangle, we'd have delta x times f of a plus, the next one would be a plus delta x times 3, or 3 delta x, right? And then we can keep on going to the very last rectangle, right? The very last rectangle would be delta x times f of our very last rectangle would be B, right? That would be B, which is also A plus delta x times n, our number of rectangles, correct? So delta x times n should be B, right? So that would be a way to write, a very, very general way to write that approximation for the area under the curve using a right Riemann sum. Okay? Now this is a little tedious here, so I'm going to write this sum. I'm going to write this sum using summation notation. Summation notation. So we have this 2 and this 3, the next one will be 4 and 5 and 6 all the way up to n. So I'm going to use a counter of the letter I. I could use k, j, those are common counters, but I'm going from 1, this one was 1 here, and I'm going to go all the way up to n, right? Delta x, I think I'm going to put delta x in the back. I'm going to write the function first, f of a plus delta x times I times delta x, right? And I could write that as, I'm just going to write it like that. I could change delta x and write it as this b minus a over n. I could do that. Should I do that? Maybe I should do that. F of a plus b minus a times I over n. So I'm just replacing delta x with b minus a over n. And then b minus a over n is delta x. Okay, so this is, go back to my approximately equal to sign if I'm rewriting that over here. So that's my approximation. That's my approximation. Now, how can we, what would happen, what would we do to get a better and better and better approximation? What would be happening to get a better and better approximation? To get a better and better approximation, we need to increase the number of rectangles, correct? What if we did the impossible? And what if we had an infinite number of rectangles? If we had an infinite number of rectangles, then we would have the exact area under this curve. So this approximately equal to sign would no longer be approximately equal to, it would be equal to the limit as n goes to infinity, the number of rectangles goes to infinity of this guy. The sum, whatever counter you want to use, it's going to go from 1 to n. But again, a lot of times I'll see a k or a j there for the counter. I, k, j tend to be good counters, often used counters. A plus b minus a over n times I usually put that I up on top, times b minus a over n. Remember, that was our delta x right there. And this is what I was going for. How long did it take me? About 9 minutes. Okay, that's what I'm going for. This is something that I need you to know, and I know that that sounds insane and crazy. I'll show you some ways. I'll show you some tricks of the trade to remember. Okay, this is the limit of the sum. The limit of the sum. The limit of the Riemann sum. Okay, because this we got from the right Riemann sum. Okay, notice that our dx is taking the place of our delta x. Then we have our function. So in place of this x goes my expression that we made for our x value. That came from our each x value, right? So It's really the same thing. These are the same exact thing. All right. This is a big deal. This was a big deal when they did it way back when. Okay, let's take a look at some examples now. Take a look at some examples. All right, so let's write this integral as the limit of a Riemann sum. So I'm going to write this as the limit, and kids sometimes say, I always forget if limit or the summation sign goes first. I'm like, well, it's a limit of a Riemann sum. Limit of a sum. So limit comes first, sum comes second. So limit, the number of rectangles is going to infinity. The n is going to infinity. Number of rectangles. And then here comes your Riemann sum. Sum counter, I'm going to use I. And this is counting the rectangles. So we're going from the first rectangle to the last rectangle, and the last rectangle is n. Okay? Now here comes our function. Well, our function is x squared plus 1. But in place of x, I'm going to write this up here. In place of x, right? And remember, this came from the x value for each rectangle. A plus change in x, it's delta x, I, delta xi, where delta x is the change in x, b minus a over n. So 7 minus 3 is 4 over n times I, 4i over n. So in place of x, we're going to write this. So we're going to have a is 3. I should have written that as a 3, not a. This is a plus b minus a over n times I. Okay, 3 plus 4i over n. The x is being squared. We're adding 1. And now we need to multiply all of this times our delta x. B minus a over n. 4 over n. Remember, delta x is b minus a over n. And that's it. Let's do another one. Limit as n goes to infinity. Well, first of all, notice that they have it as 8 to 2. 8 to 2, we could change this and make it a negative 2 to 8. But since they wrote 8 to 2, I'm just going to go with it. All right? So the limit, sum, this time, well, I'm going to stick with I, 1 to n. Next time I might change to k or some other letter. 1 to n. All right. Sine of x. Well, in place of any x, I'm going to write that. In place of every x, I'm going to write that. So what is a? A is 8. Okay. What is b minus a? Well, b minus a is a negative 6. So instead of writing a plus something, this is going to be a minus something because 2 minus 8 is negative. So 6 I over n. So in place of x, that's what I'm going to write in here. I have another x, so I need to write that same thing again. And then we multiply the whole thing by our delta x, b minus a over n. That's it. Number 3. Limit n goes to infinity, number of rectangles goes to infinity, sum. This time I'm going to use a k just to show you that you can use different letters here. 1 to n. All right. I have 3x squared. So I have 3 times, in place of the x, I'm going to write A here is just 0. So if you want to write 0 plus, you can, but I'm just going to leave that a blank. 0 plus b minus a is 5 I, not I, I'm using a k, so k over n squared for the 3x squared minus, again, 5k over n for the x. Delta x is going to be just 5 over n. No k in that. No k in delta x. Because that's not, there's no need to count that. So that's it. You can use I, K, and J for those. AP does. I've seen AP use I and K a lot. All right. 4a. Let's write this as a limit of a Riemann sum. So limit, number of rectangles is going to infinity, sum, I'm going to go back to I, 1 to n. Okay, natural log of, in place of x, we're going to write b minus a over n times I, right? Well, b minus a is 2, so in place of, oh, I forgot my a plus. A plus that, so 3 plus that, okay? So in place of x, I'm going to write 3 plus a plus b minus a I over n times just the 2 over n, no I, just the change in x, delta x, which is b minus a over n. Okay, let's do this one. So a here is 0, b minus a is still 2, I over n. So that's going to go in place of x, okay? So we're going to have limit summation natural log of 2i, oh, I'm sorry, I forgot the 3. They have a 3 right here. So 3 plus x is 2i over n times just my change in x over n. It ended up being the same thing. Okay, let's write this as a limit of a Riemann sum. Limit okay, I have a 2 way out in front, so I'm going to write a 2 way out in front. Okay, so this time, in place of the x, I'm going to write a plus b minus a is just 1 I over n. Okay, so I'm going to have natural log 3 plus 2 I over n times my change in x is just a 1 over n. Okay, now what can we do with this? Well, we can clean this guy up right here and make it 2i over n. This 2 we can multiply in. Just multiply it in. So this would be limit n goes to infinity, natural log 3 plus 2i over n times, I can put the 2 here, I can multiply it by this, I think I'm going to multiply it by that, because if I do, now I see all 3 of these. can be written using the same limit of a Riemann sum. All three of these definite integrals have the same limit of a Riemann sum. Let's think about this. If we take the integral, Math 9, 3 to 5, 5, of natural log x, I get that decimal. Let's go and do this one. Math 9, 0 to 2, natural log 3 plus x. Same value. 2, Math 9, 0 to 1, natural log 3 plus 2x. Same value. So these look like three very different integrals, but as it turns out, they give the same value. They have the same value. All right. Number 5, little multiple choice question. Which of the following definite integrals are equal to this limit? Let's find out. Okay, well, let's see. In number 1, now, keeping in mind what we just did, that may have given things away. But here's my thought process. If I'm just doing this, I'm thinking, okay, that number that's first thing in the parentheses could be A. That could be A. So it could be integral -5 is my A value. If I add 6 to -5, I should get my B value. So -5 plus 6 is 1. Right? And the function looks like tangent of x dx. So that's one way to do it. And that's written right here. So I know that that is one of them. Okay? Now let's see if these two also will work. Let's see. So if I was writing the limit of a Riemann sum for this, I would say limit and then summation. And since this is a multiple choice, I'm not going to use all the bells and whistles. I'm just going to call it lim sum, which, by the way, is a thing. Lim sum of tangent. Okay, I'd have the -5, and then in place of x, I would have change in x over n times I. So 6i over n, right? Times change in x over n. And that's exactly what they have written here. So that works. Okay? Let's do this one. And I know that there's a 6 outside. I'm going to save it and multiply it through at the end, just like we did for this one. Okay? So I'll still have the limit times of the summation, lim sum, tangent, -5 plus 6, and now in place of x, I'm putting 1i over n. 1i over n times 1 over n. 1 over n. But now I'm going to pull in the 6 and make it 6 over n. And again, that's the same thing. So all three of these work. Kind of crazy, huh? All right, number 6. For what value of k does this integral equal this limit? Well, I find the k. K is the lower boundary. I know where to look for a lower boundary. Lower boundary is usually that first number in the parentheses. So I'm thinking that k is 6. I'm thinking k is 6. But let's make sure it works, because as we saw up here, they can do some funny things with it. This is not always that lower boundary, right? So let's see. If this is a 6, then 14 minus 6 would be 8. That would be up on top of my part of my x here. So there is an 8 there. So 6 plus 8 is 14. 6 plus 8 is 14. It works. So k is 6. The lower boundary is 6. Okay, another example. Number 7, let's write this limit as a definite integral. Write that limit as a definite integral. There's not just one answer here, right? But we're going to write some definite integral. So it's going to be integral. All right, my question to you is, what would you like your lower boundary to be? Well, my go-to, when I see these 5s here, as this parentheses, my go-to is to let that be my a value. So I'm going to let my lower boundary be 5. If I do that, I add 2 to get my upper boundary. Add 2 to get your upper boundary. And now, each of these guys is x. Each of these guys is an x. So that's going to be x cubed plus 3x dx. If you want to put parentheses there, do it. If you don't want to, you don't have to. They're assumed. Once you put the dx, we know where it ends. Okay? So that will work. It's not the only thing that will work, though, because we could have also said, where it says 5 plus 2I over n, where it says that, I could have just let this be x. And if that's x, then my function's going to be 5 plus x cubed plus 3 times 5 plus x dx here. And if that's true, if this is my x, then I'm starting at 0 because there's nothing plus here, right? And I'm going to 2 because 0 plus 2 is 2. So that'll work. It's not the only one that'll work because we could have put like one of these to be the a value and stuff. So there's lots of different ways to do it. This is my go-to. That's the one I go to. All right. Let's write this one as a definite integral. So integral, I know what my function is. If I let this be x, my function is just ln of x. There's my dx. Okay. My a value, my bottom boundary will be 2. I add 3 to 2 to get my upper boundary, and I'm done. Not bad. It's not the only one, but that's the one I'm going to write. If I'm given a choice, that's the one I'm going to write. Okay. A region is bounded by the graph of y is equal to 4 minus 3x squared, y is equal to 0, x is equal to 0, and x is equal to 2. So we have some curve, and it's bounded by these guys. Which of the following is the area of that region? Well, first of all, we're going from 0 to 2. We're going from 0 to 2. So the integral will be from 0 to 2 for x. Okay? I know what my function is. My function is 4 minus 3x squared. So here's the integral that gives that area. Now I just want to write this integral as a limit. Okay? So in my mind, I do my limit, my lim sum of 4 minus 3 times something squared. I'm going to put the appropriate thing in for x. So in place of x, I'm starting at 0. I'm starting at 0 and I'm adding 2. So this would be a 2I over n. And then we're going to multiply by just 2 over n. 2 over n. Okay? So let's see if we can go find that. Let's see. 4 minus 3. No, not the 1. 4 minus 3, 2I over n. Is this right here? I think this is it right here. It looks right to me. B. Yeah, the other ones are not correct. Okay, number 10, last one. Which of the following expressions is equal to this expression? Well, I see that they wrote out this sum, they expanded that sum. I'd like to write that as a sigma. It'll be easier for us to see what's going on, okay? So that will be the sum of sine of 3 plus, started with 1, 2, 3, all the way up to n. So that's going to be my I over n. So I is going from 1 to n, okay? And there's nothing else with it, so that's just it. So in place of what's in these brackets, I can write this sum. This 1 over n, we usually see out and back, so I'm going to go ahead and put that in. Okay? And then the limit. So I just cleaned up what they gave me and made it something that I'm more comfortable with. Now from this, they want us to change it to a definite integral. So if I was just writing this as a definite integral, I see that 3 and I want to put my lower boundary as a 3. I add 1 to it to get my upper boundary. And my function would be sine of x dx. So that will work. But it's not over here. That is true, but it's not the one that they chose. So I see other sine x's in here, but if it's just a plain sine x, it has to have these boundaries. So I know these are not going to be my correct answers. The other answers have this 3 plus. Oh, there's one down here too, a plain sine x, which is also not a 3 to 4. So I know it can't be B, C, or E. So it has to be A or D. So they clearly have left this 3. So that's fine. We can do that. That means I would have the integral of sine of 3 plus x dx. So in place of x, I have just that. So a here has to be a 0 because there's nothing being added. And then for the x, that would be 0 plus 1i over n. So this has to be a 1 because 0 plus 1 is 1. So 0 to 1 of sine of 3 plus x dx will work. D. Confusing? A little bit. Yeah. But when you try, this is a challenge. I get that. But when you do several of these, I think that they're fun. It's like a puzzle, trying to figure things out, trying to find the connections, sort it out. So probably one of the first topics that we do that's very conceptual. So some of you will do quite well on this, I'm sure. Some of you will struggle a little bit, but hopefully you'll grasp it in the end.